Now let's see what we have in the case of a massive Dirac field. Now we had already seen that in the massless case we have two equations, E minus sigma P phi is equal to 0. We said that this is the, for the positive energy solutions, this is the right helicity, positive helicity, which we also call the right-handed, and then we have E plus sigma dot P for phi L. This is equal to 0. This is in the case of massless particles. Now, if we have massive particles, one might be tempted to say, to just say that each one is m times itself with some coefficient. But this doesn't actually work because this doesn't satisfy the energy momentum relation. You see, we had seen that the Dirac equation can be first order Dirac equation can be written as E phi is equal to alpha I pi plus beta m phi, for which alphas satisfy alpha I, alpha j is equal to Kronecker delta ij, alpha I beta is equal to 0, and beta squared this is equal to 0. Now in the 2 by 2 case, we could identify alpha I to be plus or minus sigma I, but unfortunately there is no force matrix beta, 2 by 2 matrix beta in this case, so we have to go to a higher dimensional matrix representation. Now to determine, one can think that maybe one can go to 3 dimensions, but that doesn't work because these commutation relations imply that alpha I squared and beta squared, they are all 1, which tells us that the eigenvalues of alpha I and beta are all plus and minus 1. If one looks at the sum of the eigenvalues, which is the trace, let's look at trace of alpha I, which is the trace of alpha I beta beta, because beta squared is 1. And now we can use the property of the traces. If you have the product of two matrices inside the trace doesn't change if you just exchange commute these matrices. Note that this doesn't generalize to more than the product of more than two matrices. This is only valid if we have two matrices, product of two matrices. Now if you look at over here, this is the matrix A, this is the matrix B. So this can be written as trace of beta, alpha I beta. This is just using the properties of the trace. Now we can use the properties of the alpha and beta matrices. Beta and alpha I, they anti-commute. So this is trace of minus alpha I beta, beta. But now beta squared is 1. So this is equal to minus trace of alpha I. So we started with trace of alpha I, and we have shown that this is minus the trace of alpha I. Well, this basically tells us that trace of alpha I is equal to 0. And similarly, for the trace of beta, one can do essentially the same tricks. So this is trace of beta, alpha 1, because alpha 1 squared is also 0. Now using the property of the trace, this is alpha 1, beta alpha 1. Now using the property of the beta and alpha, they anti-commute, this is equal to trace of minus beta, alpha 1, but this is 1. So this is minus trace of beta. So we see that trace of beta is equal to minus trace of beta, which tells us that trace of beta is equal to 0. Now we see that the traces of these matrices alpha I and beta I are 0, but the traces, some of the eigenvalues, which are all plus 1 or minus 1, and hence we can see that there are equal number of plus 1 eigenvalues and minus 1 eigenvalues, and hence the dimension of these alpha i's and betas has to be even. Alpha I can be 2 by 2, alpha I and beta 2 by 2, or 4 by 4, or 6 by 6, etc. The lowest dimension will be just 4 by 4. But rather than trying to find these alpha i's and beta in 4 dimensions, let's just try to modify these equations. So we have already these two equations in such a way that we obtain a relativistic equation. So we have the E minus sigma dot P phi L. This is, we will modify this one, and E plus sigma dot P. Now this is R, this is L. So let's look for an equation for which this is given by some coefficient times mass times phi L, and this is given by m phi R. Note that I'm not putting any arbitrary coefficient over here, because if there were some coefficients over here, I would just multiply phi L by a suitable constant, so that that coefficient would become 1, and it would just modify this eta, which we already don't know. So we will be choosing eta such that this coefficient over here will be 1. First, let's see that if this will give us the correct energy momentum relation. So let's just take this the first equation and apply this matrix to the first equation. So we have E plus sigma dot P, E minus sigma dot P acting on phi R. This should be equal to E plus sigma dot P eta m phi L. But I know how this matrix acts on phi L, so this is eta m squared phi R. If I multiply these operators over here, I will get E squared minus sigma dot P squared phi R. But this is just P squared. So what we obtain is E squared minus P squared phi of R should be equal to eta m squared phi of R, which tells us that eta is actually 1, and we do have a relativistic equation. E squared minus P squared is equal to m squared. So now we have since these phi L and phi R were just had 2 dimensions, this here we have a if we combine phi L and phi R into psi, this is a 4-dimensional spinner. Now let's write the equations. This is m phi L and E plus sigma dot P. This is phi L is equal to m phi R. Now we can combine both of these equations into a single equation in using this psi. So this single equation is E plus sigma dot P, E minus sigma dot P. These are zeros. Phi L, phi R. This is equal to m 0, 1, 1, 0. Phi L, phi R. Well, what this matrix does is it just exchanges this phi L and phi R. Well, in the first line we get the phi R, in the second line we get the phi L. So this is our 4-dimensional Dirac equation for a massive particle M. Now we can convert this into the Dirac form. You see, this equation can be written as E of psi minus pi minus sigma I 0, 0, sigma I psi. This is equal to m 0, 1, 1, 0 psi, or E of psi is equal to minus sigma I 0, 0, sigma I psi plus m 0, 1, 1, 0 psi. Now in our original Dirac equation, we said that E acting on psi should give us some alpha I p, here there is the pi, alpha I pi plus m times beta psi. So we can just read what alpha I is and what beta is. So we see that beta is equal to 0, 1, 1, 0, and alpha I is actually minus sigma I, 0, 0, sigma I. Well, let's just check a couple of the properties. Beta squared is 0, 1, 1, 0, but keep in mind that this 1 over here, these 1s, are actually themselves 2 by 2 matrices. So this is times 0, 1, 1, 0. This is 1, 0, 0, 1, and hence it is actually 1. So beta squared is 1. Let's calculate beta alpha I. 0, 1, 1, 0 minus sigma I, 0, 0, sigma I. This is 0, sigma I, 0 minus, this is 0, this is sigma I minus sigma I, 0. Now let's look at alpha I beta. This is minus sigma I, 0, 0, sigma I, 0, 1, 1, 0. This is 0 minus sigma I, sigma I, 0, which is just minus beta alpha I. So they do anti-commute. So all the properties, matrices alpha and beta, they satisfy all the properties, and you can just show the remaining properties, all the properties of the matrices alpha I and beta that they should have. So now we have found the representation of these alpha I and beta matrices. Now we can convert this into the conventional Dirac equation just as we did before. So the equation by multiplying beta P0 minus of beta alpha I Pi minus m psi is equal to 0, or we can write this as gamma 0 P0 minus gamma I Pi minus m psi is equal to 0. Let's write down these gamma matrices. Gamma 0 is just beta, which is 0, 1, 1, 0. Gamma I is beta alpha I, 0, 1, 1, 0, times alpha I is minus sigma I, 0, 0, sigma I. So gamma I is 0, sigma I minus sigma I, 0. Or we can write the gamma mu matrix. Now gamma mu, for each mu is a matrix, and it can be written as 0, sigma mu, sigma bar mu, 0, where we had defined this sigma mu matrix as 1 minus sigma I, and sigma bar mu, this is equal to 1 and sigma. Now gamma I, here we have there, okay, here there is the minus sign, and gamma bar mu is 1 sigma. No, sorry. So gamma 0, okay, so let me rewrite it. Gamma 0 is we can write this as gamma mu p mu minus m psi, where gamma mu is gamma 0, gamma I, and gamma 0 and gamma I are given in this form, and this can be written as 0, okay, now it's fine, sigma mu, sigma bar mu 0, where sigma mu is defined as, if mu is 0, it's the identity matrix. If mu is ijk, it is just the Pauli matrices, and sigma bar mu is 1 and minus sigma. So this is our representation. Now let's try to find the solution, the explicit solution. We have the gamma matrix now, and we can find the explicit solutions of the Dirac equation for this representation. Keep in mind that the only property that is fixed about these alpha matrices is that they should anti-commute with each other. Okay. So any four matrices that satisfy these properties over here, these properties, you can just use. But of course, depending on which representation you use, there is physical interpretation of various components of phi L and phi R, or various components of this psi matrix we had defined over here will be different. But as long as you are consistent with the representation of gamma matrices you use and the physical interpretation, everything should, all the physical predictions should be valid. Now in this representation, let's now find the explicit solutions. Now keep in mind that we are looking for solutions of psi which looks like e to power minus I px. This is phi of x. This is, let's just write it phi of p, just plane wave solutions. And once we, this psi of p should satisfy p slash minus m, psi of p is equal to 0, where we had defined this p slash, which will be used frequently as gamma mu p mu. Now we already had seen that for these particles p squared should be equal to m squared. Now I will keep denoting E as the positive energy, p squared plus square root of p squared plus m squared, but p0 can take two values. P0 is either plus E. In that case, I will just denote psi of p as u of v, u of p, and p0 can be minus E. In this case, psi of p, I will just represent it by v of p. Now first let's look at the explicit solutions of p0 for p0 is equal to E. The equation we have is p slash minus m, u of p should be equal to 0, and remember gamma mu has the representation 0, sigma mu, sigma bar mu 0, and so this equation can be written as the diagonal elements are just minus m, p sigma bar. These are just a four-dimensional p sigma, the scalar product, and at the same time they are just 2 by 2 matrices. Multiply by ul, ur. This should be equal to 0. So if you write it explicitly, minus m u of L plus p sigma u of r is equal to 0, and p sigma bar u of L minus m u of r is equal to 0, or m times u of L should be equal to p sigma u of r, p sigma bar u of L will be m times u of r. And we have to find the general solution of this equation. Now before proceeding, let's look at what p sigma times p sigma bar is. Now first of all, these things commute. Their commutator is 0. Well, the easiest way to see that is it's just p0 minus p sigma, and this is p0 plus p sigma, and p0s commute with everything, p sigma commutes with p sigma, so they do commute with each other. So that will simplify the fact that they commute with each other. we'll simplify the computations, because in most computations we can just treat them as if they are ordinary numbers, as we will see in a moment. And let's take their product, P sigma bar. This is equal to P0 minus P sigma, P0 plus P sigma, or this is equal to P0 squared minus P sigma squared. But P sigma squared is just P squared. So this is just M squared. Now let's go back to our solution over here, in the solution of these two equations. So let me just, instead of these m's over here, let's start with the first one. Instead of m, I can just put square root of P sigma bar, U of L is equal to P sigma U of R. Well, I can cancel this P sigma with one of the square roots over here. So this is the equation. This is the first equation. P sigma bar U of L is equal to square root of P sigma U of R. Well, here these are matrices, but I just treated them as if they were ordinary numbers at this step over here. That I can do because they commute. And similarly, if we look at the second equation can be written as P sigma bar U of L is equal to square root of P sigma bar P sigma U of R. Well, note that here I just commuted their position, but I can do that because they do commute. Now I can do the same trick. This will cancel one square root from here. So we get square root of P sigma bar U of L is equal to square root of P sigma U of R. You see, both equations, they lead to the same result. Now we can write the solutions of this equation. U of R can be, the general solution will be P sigma bar times Xi, and U of L will be P sigma Xi being the same matrix. So basically U of R is proportional to this thing multiplied by some unknown constant, and U of L is this thing multiplied by some constant. So if U of R and U of L satisfy this relation for an arbitrary Xi, then they will solve this equation and hence this equation. So these are our eigenvalues. So Psi can be written as square root of P sigma Xi and square root of P sigma bar Xi. So this is the general solution. Now you see, Xi can take two independent values, so we have two independent solutions of Psi. Well, this is a 4x4 matrix equation that we are solving, but we obtain only two equations. But keep in mind that we are looking at the case when P0 is equal to E. We are looking at the positive energy solution. Now let's continue further. This is U, not Psi. I had used the notation U of P. Let's look at the normalization. U dagger of P, U of P, this is equal to Xi dagger, square root of P sigma. Note that sigma is a Hermitian matrix, so we just change their position. And Xi dagger, square root of P sigma bar, square root of P sigma Xi, square root of P sigma bar Xi. So we get, this is equal to Xi dagger P sigma Xi plus Xi dagger P sigma bar Xi, or which can be written as Xi dagger P sigma plus P sigma bar psi, but this sum is just twice p0. So we get u dagger of p, u of p is actually equal to twice p0 psi dagger psi. Now we will choose the normalization of psi's such that psi dagger psi is equal to 1, which gives us u dagger of p, u of p is equal to twice p0 or twice energy corresponding to 3 vector p. Now let's look at this normalization is obviously not Lorentz invariant. Let's look at one more combination. Let's look at u dagger gamma 0 u. Well, u dagger is psi dagger square root of sigma p, and psi dagger sigma bar p. Gamma 0 is 0, 1, 1, 0, and u is square root of sigma p psi square root of sigma bar p psi. So we obtain, let me just first multiply these two over here, these two. If we multiply those two, we get sigma p psi dagger sigma bar p sigma bar p psi sigma p psi, which becomes psi dagger sigma p underscore root sigma bar p psi plus psi dagger sigma bar p sigma p psi. Now you see in these two terms, sigma and sigma bar, their positions are different, but we know that sigma p and sigma bar p, they commute with each other, and so these two terms are the same. And you can also say that since this product is m equal to m squared, so the square root is m, so this is 2m psi dagger psi, which is equal to 2m. So you see that u dagger gamma 0 u is equal to 2m, which is a Lorentz scalar. Now this is a common expression that we always see when we work with spinors. So you take the dagger of the spinor and multiply it with gamma 0. So that is also given a special name. This is u bar is defined as, this is called the Dirac conjugate, and it is defined as you take the dagger and then you multiply it with gamma 0. This is the definition. Now let's look at the negative energy solutions. So we have P0 is equal to minus E, and psi of x, we are looking for a solution of the form e to the power. We started by looking at minus I px, v of pv, but let's write it in this form. This is e to the power I e of t plus, or let's see, minus k of x v of k. Now what we k0 is e, it is still positive energy, and k is, in this definition over here, k is actually minus b. So let's look at what v is. Now the equation we had is the energy operator multiplied by gamma 0, or let me write it in this way, p slash minus m psi of x is equal to 0. Now when p0, the operator, acts on our psi of x, it gives us minus e psi of x. And similarly, p acting on psi of x gives us minus k psi of x. So v of k actually satisfies this equation, k slash plus m V of k is equal to 0. This is the equation satisfied by V. And to compare it with the previous result, note that U satisfies the equation if its momentum is called P, P slash minus M is equal to 0, whereas V satisfies K slash, or we can also rename K, P slash plus M. V of K is equal to 0. Well, we can just find the solutions of V of K just like we did in the case of the U of K, but note that the solution can be obtained in a kind of a straightforward manner. You see, V of P satisfies this equation, whereas U of P satisfies P slash minus M. U of P is equal to 0. Now, if you compare these two equations, you see that their difference is that the momentum operator, momentum matrix appearing over here, it changed its sign. So we can just solve for V of P, and it will be just U of minus P. But rather than taking this shortcut, let's calculate it explicitly. Now P slash is 0, P sigma bar 0. So P slash plus M V of P, this is equal to M P of sigma bar 0, V of L V of R, now this is M, this should be equal to 0. So M times V of L should be equal to minus P sigma times V of R, and P sigma bar times V of L is equal to M minus M V of R. We know that both of these equations will eventually give me the same equation, so let's just pick up one of them. Let's take the second one. P sigma bar V of L is equal to minus square root of P sigma bar P sigma V of R. So this is square root, this P sigma bar under the square root just cancels one square root over here. So we get square root of P sigma bar VL is equal to minus square root of P sigma VR. So we can, just like in the previous case, we can write the general solutions. VL will be equal to P sigma, square root of P sigma multiplied by some arbitrary constant spinner, and V of R will be equal to minus square root of P sigma psi, or V of P is given by P sigma psi minus P sigma psi. Let's again check the normalization of this V dagger P of V of P. This is equal to psi dagger P sigma psi dagger. Now this is P VR is sigma bar square root of P sigma bar square root of P sigma psi. Now this is minus square root of P sigma bar psi, which is equal to psi dagger P sigma psi plus psi dagger P sigma bar psi, which is again twice P0, or twice E0 in fact, E of P psi dagger psi is 1. Well, we can also calculate V dagger P gamma 0 V of P. What this will do is gamma 0 just exchanges these two parts of the four-dimensional spinner. So this is equal to psi dagger P sigma minus psi dagger P sigma bar minus P sigma bar psi P sigma psi, so this just becomes minus 2m. And it just, as before, this is defined as v bar v of p. V bar of p, v of p. Now finally, let's also calculate what is v bar of p, u of p. Now v dagger of p is psi dagger, square root of p sigma, and minus psi dagger, square root of p sigma bar. This is a v dagger, and we multiply by gamma 0, 0, 1, 1, 0, and then we put u of p, which is square root of p sigma, psi, square root of p sigma bar, psi. So this will give us psi bar p sigma minus psi bar p sigma bar under the square root psi p sigma psi, which is psi dagger p sigma bar under the square root psi minus psi dagger p sigma bar p sigma psi. Now note that this product is just m under the square root, and this square root is also m, so this is just 0. So v bar of p and u of p are orthogonal to each other in this sense. Now you can just go ahead and calculate u of p and u bar of p and v of p. This will also be 0. Now before concluding this video, let's also look one more thing. We will be taking quite often the Hermitian conjugates of various expressions. So we also need the gamma mu dagger. Now gamma mu is 0 sigma mu minus, no, sigma bar mu 0 dagger. Now this dagger is taking the transpose and the Hermitian conjugate, so this will become 0 sigma mu dagger, and this is a sigma bar mu dagger. Now note that sigma matrices, the sigma mu and sigma bar mu are just sigma matrices and the identity matrix, so they are Hermitian, so this is just 0 sigma bar mu sigma mu 0. Now what this tells us is gamma 0 dagger is gamma 0, gamma I dagger is minus gamma I. So it's because the sigma and sigma bar, they differ in their space components by this minus sign. But note that this minus gamma I, we can also write it as minus gamma 0, gamma I, which is minus gamma 0, no, not minus, gamma 0, gamma I, gamma 0. So here I use the fact that gamma 0 squared is 1, and in this step I just exchanged this gamma 0 and gamma I, which brought another minus sign. And gamma 0 is actually gamma 0, gamma 0, gamma 0, because this gamma 0 squared is 1, we are left with just gamma 0. And hence we can combine these two results, and gamma mu dagger would be just gamma 0, gamma mu, gamma 0 for any gamma mu. Now this we will be needing in the future.